Please join me in welcoming to the Distinctive Voices podium, Dr. Jonathan P. Stewart.
Thank you, Jennifer, and thank you for the invitation to come here. It's a pleasure to speak to you all at this Distinctive Voices seminar series. I'm an earthquake engineer, as was mentioned, so I think we're all Californians here, right? So we recognize that earthquakes are a threat to us. I think as Californians we have a general awareness of that. Most of us have experienced multiple earthquakes during our lives here, unlike some of our friends in the central U.S. or the East, except perhaps those in Oklahoma or recently Virginia. But we get more. But despite that general awareness of threat, I find in talking to non-experts throughout the state that there isn't necessarily an awareness of what are the most serious risks. What are the risks that actually are almost existential for us as a civilization on the West Coast? And as an earthquake engineer, I worry about things like that, and that's my job. And at the top of my list is the risk to the water system that we have. And so over the course of the next 45 minutes or so, I'm going to try to explain why I'm worried about this, and explain also some of the things that the state, the local governments here in Southern California and elsewhere are trying to do to address these things. Before I go further, I do want to acknowledge that I'm presenting the work of many people. This is not just me. So we've had support from NSF and the state, California Department of Water Resources, over the years doing this. The second bullet is several faculty who've been involved in this work. Ann Lemnitzer is a professor here at Irvine. A number of students and postdocs have worked on it. And the last bullet is many professionals with the state, with various utilities, practicing engineers, and also people actually overseas. Tsushi Mikami works in Japan. Ruben Jonganyan is in Netherlands. So we're working with people actually from around the world who face similar sorts of threats. So the outline of what I'd like to accomplish today is listed here. So the word resilience is in the title. I'm going to explain what I mean by resilience as it's applied to water systems. Then I will get into some detail of the resilience of California's water supply systems. So these are the systems that bring water from the source, typically the mountains, to where we need it, which is in our agricultural areas and our cities. As I go through that resilience of the water system, I will make the point that one of the most vulnerable links in that system is the Bay Delta region. I'll explain why that is, and I'll explore the nature of that risk in a little more detail, and then I'll conclude with some comments on risk mitigation. Okay, so it's first useful, I think, to talk about what do we actually mean by resilience. As it says here, it's basically the capability of a system to maintain some functionality after a stressing event. And we actually expect damage. This is kind of a constant throughout earthquake engineering. We don't design things typically, a few exceptions, we don't design things to be undamaged. We actually expect things to be damaged. What we are hoping is that we can recover quickly from that damage, and we don't lose functionality for an extended period of time. Okay? So the graph on the right is functionality in sort of a dimensionless sense, from 0 being not working at all, 1 is fully functional, and how that changes over time. And if there's no earthquake, there's no event, we muddle along at a functionality of 1. When we have a serious event that's called a disaster, we lose functionality. So as I say, we can't really avoid that. There is going to be some losses. As I use the word disaster, it's bad, but it's not so bad because from a resilience point of view, we recover quickly, in the order of, let's say, weeks. So there's effects, but the society can go on. We don't have massive long-term impact. So I'll show you an example of that, which is actually the Northridge earthquake from 20 years ago. Catastrophes are different. Catastrophes are, as the word suggests, it's something that is unacceptable. We should not be having catastrophes. We should be engineering our systems to avoid that, because whereas you may have the same level of initial damage, it takes a lot longer to recover. Okay, so what resilience is really about is like the area underneath this curve here, within this curve. Small area here, big area here. And the larger that area is, the less resilient our system is. Now, we're talking about this specifically in the context of water systems, and there's a lot of ways you can measure that functionality. Okay, so the metrics that are used by the City of Los Angeles, which operates the Department of Water and Power, are listed here. So, for example, water delivery. That basically means you turn on the tap, does anything come out, okay, after the earthquake? Water quality, can you drink it? You may be able to get some water out of your tap, but if you can't drink it, that obviously limits the usefulness. Quantity, does everybody get what they need? Fire protection, that's pretty obvious. We need to have some degree of pressure to the fire system, even if people can't open their tap, where we obviously have terrible consequences with post-event fire. And then functionality is it really working at the full capability that we would like? And that's usually going to take a lot longer to get to. So let's walk through an example of this. Northridge earthquake, 1994. Some of you may have felt it, experienced it. It was at 4:30 in the morning on January 17th. The map here is showing the surface projection of the fault. This is the San Fernando Valley, Santa Monica Mountains. LA is here. It started here and ruptured to the north. The areas that had the worst shaking were northern San Fernando Valley and Santa Clarita. It did not actually break the surface, so it's called a blind thrust fault, but it did produce locally some pretty intense shaking. 57 people died, and there were over $10 billion with a B in damage from this event. Like I say, the effects were most severe up here, but it was felt broadly, and there were some local effects elsewhere as well. Now, looking at the water supply system, this is a map that is showing where pipes were broken throughout the San Fernando Valley and the northern part of the LA Basin as a result of the Northridge earthquake. And an interesting fact is that this earthquake was the most damaging event for a water supply system, water distribution system, in the United States since 1906 San Francisco earthquake. So some of the nature of that damage, water systems, once they get into an urban area, consist of trunk lines. These are major pipes that are distributing large amounts of water, and then a distribution that goes out to that down individual streets to businesses and homes. And they had 74 breaks in the large trunk lines, so that led to major losses of pressure in parts of the San Fernando Valley. And there were over 1,000 breaks in distribution lines throughout the city. So that sounds pretty bad. And they were having some loss of functionality early on. A couple of the breaks were particularly dramatic. So this is Balboa Boulevard in the northern San Fernando Valley, where major lines run through this, both gas lines and trunk lines. And this street actually had a displacement of about 1 meter to the south as a result of softening of the soil caused by the earthquake and movement on a very mild slope down the hill. That broke the gas line. It also broke the water line. The gas line was ignited when the owner of that truck came out and tried to start it. Of course, you start something with spark plugs, right? The spark with the gas line doesn't work well. So that led to this explosion, And you have this juxtaposition that could only happen in LA with fire and water all together in the same place. And that was an image that was on the cover of the LA Times at that time. Why did that happen? Well, that was an old pipe. It was a brittle pipe. It could not sustain the displacement of the ground around it, and so it did what it's going to do. It broke, and it broke in several places. We have pipes like that throughout the area. This is not a unique occurrence, and we can absolutely expect things like this to happen when we get other Northridge-type events in the future. What this is showing, and this is from Craig Davis at the LADWP, is those resilience curves that I showed initially in a schematic form for the different types of functionality that I described. So here's the functionality. This is time in days, notice. Okay, so it's going from 1 day to about 2 weeks. This would be normal, and you have the stressing event here, Northridge. They were able to get water delivery back to essentially full capacity within about a week, which was pretty amazing. They did not have all the lines fixed by that time. They were able to do that by tapping into alternate sources, some groundwater pumping, for example, to get water into the system downstream of where the breaks were, to recharge the system. Quantity was right behind. So initially they didn't have the quantity, but just a few days later they more or less had the quantity that they had had before. Fire protection was restored reasonably soon. Quality took longer. So there was boil orders that were essentially in place. So you could turn on the tap and have water, but you couldn't actually drink it. So that took a little longer. And full functionality actually went on many months, even more than a year, as they went back and systematically repaired all these lines and got everything back to where it had been prior to January 17th. Now, a point I want to make before moving on from Northridge is that that event, to an earthquake engineer, is not all that extraordinary. In fact, while that particular fault, we don't expect to be producing earthquakes on a decades or even a century type of time scale, probably be more like thousands of years. There's so many faults like that throughout Southern California that when you look collectively across the region, we can basically expect Northridge-type earthquakes every few decades, and the record more or less bears that out. That's pretty much what we get. So these sort of small earthquakes, again, to an earthquake engineer, a mid-6 earthquake is small. So the 6s to 7s we can expect to occur in approximately that time interval, and we can expect those kinds of losses. That was a disaster. It was not a catastrophe. LA went on. A catastrophe, I would argue, was Hurricane Katrina. Now, this is not an earthquake, but it makes the point about the impact of a catastrophic loss of resources. So Katrina started out as a Category 5 hurricane over the Gulf. When it came onshore near New Orleans, it was Category 3. As we all know, the levee system did not hold up in New Orleans. There were 53 breaches, and 80% of the city flooded, with over $108 billion in losses, as compared to $10 billion in Northridge. And this is one in particular, the 17th Street Canal here, where the levee actually did not the water did not actually overtop the levee. It came up against it, and the levee then slid. It was an engineering failure because of instability within the levee fill and the foundation. In fact, it's kind of a classic one. I teach my students about what went wrong with the engineering of that levee to help them understand some shear strength principles. So what were the consequences of this? Well, since we're talking about water, there was substantial loss of water service for quite a long time. They started to get some service back in place a few months later, but they didn't have full restoration for safe drinking water until over a year later, in October of 2006. Of course, there were lots of other problems in New Orleans unrelated to water. When we look at this resilience issue for the city as a whole, the catastrophic nature of this can be measured through the population loss and the related economic impact. And let me describe for you this figure, which I think makes the point. So what we have here on this y-axis is employment in the United States. This is in thousands, and this is employment in New Orleans. And these axes are scaled such that it's the same percent change from top to bottom. And this is time, starting in 2000 up to 2014. Katrina occurred here. And so we can track what's going on. So this is the U.S. employment data. And during the, say, 3 years prior to Katrina, New Orleans was more or less tracking the national trend. And then you had this dramatic loss. One could surmise that perhaps, as a first-order approximation, had Katrina not happened, New Orleans would have roughly grown like this. Now, there's been some recovery, but notice that this is over a 10-year period. So you have this huge loss here of people who left and never came back. And all the economic activity that goes along with population was lost and has not recovered, a decade later. That's catastrophic. And that's the kind of risk, I will argue, we could face here in Southern California if we don't get our act together with some of our water supply system. Okay, so the next subject is the resilience of our system. I'm going to focus here not actually on the distribution system. That's what I was talking about in Northridge, the system that distributes the water once it gets into the urban areas. I'll be talking more about the major aqueduct systems that bring the water to these areas in the first place. And this map kind of lays out the big picture of the system that we've developed in the state over time. So there are 3 major aqueducts that are providing water to Southern California. I'm not talking here about the Bay Area. In Southern California, we have the Los Angeles Aqueduct. This is the one famously built by Mulholland, bringing the water that drains off the east side of the Sierra into Owens Valley down for LADWP. There's the Colorado River Aqueduct, which is coming off the Colorado River here, and that is supplying Metropolitan Water District, or MWD. And then there's the California Aqueduct, which is coming out of the Delta. Coming down here, it has several branches that come off in various places. It feeds into LA and also comes down here towards Orange County. That is owned and operated by the California Division of Water Resources. And before going further, it's worth saying a few words about water quality in connection with these aqueducts. The water quality from the LA Aqueduct is excellent. So this is snowmelt that doesn't go very far before it gets collected and brought in. The water quality coming through the Delta is also pretty good. It's quite high quality, not many salts in it, requires fairly minimal treatment before it can be used. The water quality from the Colorado River is the worst of the 3. There's quite a bit of salt in there, and it's not usable. You can't take Colorado River water and move it out into the distribution system. The reason they use it is it gets mixed. So you mix the poor quality Colorado River water with the higher quality Delta water, and then with a little treatment it goes out. Okay, so that's kind of how the system works. You wouldn't want to have only Colorado River water, and that's a point to keep in mind as we go forward. Now, with those 3 systems having been described, let's look at each one of them as they come across the San Andreas Fault. Now, the San Andreas Fault is the plate boundary. This is the big monster fault, of course, that we've all heard of in California. They all cross it. So, again, LA Aqueduct coming through here. It's crossing it at a place called Elizabeth Lake. The tunnel underneath it is called Elizabeth Tunnel. That particular segment of the San Andreas Fault last ruptured in 1857, the Fort Tejon earthquake. And the return period, which means the average time between major earthquakes of about that size, this is high 7s, is estimated to be between 140 and 160 years. We can just call it 150. So if you do the math, we're actually a little bit overdue for that event to happen again. Now, this is a drawing of the Elizabeth Tunnel from the original design documents, and I won't have you read the numbers here, but it's basically nominally about 3 meters in diameter. Here's a picture of the construction from that time period. So remember, 3 meters. We have a pretty good idea. One of the things earthquake engineers do is we forecast risk. You know, what's going to happen when the earthquake occurs? And one of the things we have models for is how much faults move when earthquakes of different magnitudes occur. We know that by going out and looking. We measure it. And if you have a 7.8 earthquake on a strike-slip fault, there's a whole range of displacements, of course, but the average is about 5 meters. Okay, so if you have a diameter tunnel, 3 meters, and you have 5 meters, you don't have anything left, right? So this was picked up by the LA Times. Some of you may have seen it. This is basically depicting that. You got a tunnel crossing a fault, and basically, you know, it gets offset by the rupture of the fault. The water can't go through anymore, right? And this is a strike-slip earthquake. This is a dip-slip earthquake, but the principle remains the same. Okay, and then Colorado River. Now that one is coming through here. It's crossing at San Gorgonio Pass. Now that segment of the fault did not rupture in Fort Tejon earthquake. That one ruptured last in 1680. Okay, and pretty much all along the San Andreas Fault, these large earthquakes are about every 150 years. So that one's really overdue, right? That one's really overdue. It's been over 300 years. And that's the one I and all other earthquake specialists are the most worried about. We're worried about, because it's so primed, we're worried about a major rupture starting on that southern segment of the fault, perhaps near the Salton Sea, and rupturing up through this area. If we look at where the Colorado River aqueduct is crossing the fault, this is a slide that Ken Hudnett of the USGS gave me. Ken, by the way, is the advisor to the mayor on earthquake issues. He replaced Lucy Jones, who you may have heard of, who retired. So the aqueduct is coming through here, the blue line. And Ken, it's a little hard to see here, but he has drawn on the fault segments, which he himself has often mapped. He's a fault specialist. So you have a crossing here, you have a crossing here, and you have a crossing here. So one thing to appreciate if you haven't studied faults is that they're complicated, right? There's multiple branches. The San Andreas Fault is not a single plane, and this is a place where there's a number of splays, and so there's actually 3 major fault crossings of this one aqueduct, and they're all parts of the San Andreas Fault. Now, this particular structure is a tunnel, but it's not a deep tunnel like Elizabeth Tunnel. It's a fairly shallow cut-and-cover tunnel. So in that sense, it's accessible. You could get in there and try to fix it more easily than Elizabeth. But as you can imagine, Metropolitan Water is very worried about this. They consider this one of their greatest threats. Okay, and then finally, the California Water Project. They have pretty substantial hazard at fault crossings. I mentioned Colorado River has 3 of them. They have many throughout this region. That's why I drew the circle so big. It basically comes to the fault, and it kind of goes around the fault. It's crossing it multiple times as it goes along. It just turns out to be a nice route for having a good gradient of keeping the water flowing, but at the hazard of being next to and crossing the fault multiple times. This is actually one such place. So this is near Palmdale. This is the aqueduct. It's open channel. This is Palmdale Lake, which is actually a sag pond in the San Andreas Fault. It's running right through here, and they're crossing just behind this image here. In this area, it's obviously accessible, right? So if that got damaged, you could go in and you could fix it more easily than Elizabeth Tunnel, but there's many kilometers that you have to deal with. The channel is basically formed by compacted fills along here, and we could have many kilometers of these things failing. So it's fixable, but it would be a pretty substantial effort with a lot of delay to go in and do all of that. The last part I want to tell you about with the California Water Project is the intake. This is not a fault crossing. San Andreas Fault is way over here, and that is what I'm going to be developing as we move forward in the talk. That is a very serious threat up there at Clifton Court. Okay, so that leads us to the Bay Delta region. So, looking again now at California, you see this little triangle here. The reason it's called the delta is that is the shape of the Greek letter delta, right? And oftentimes river systems have deltas. So like the Mississippi River, where it reaches the Gulf, it forms a delta. It's called, it works that way because if I can just use the diagram, if you could imagine the water flowing this way, and this is a sea over here, sort of spreads out as it reaches the sea. Of course, that's not the case here. We have kind of an inverted delta. We have water coming this way, and it's draining out the end of the triangle, as opposed to coming into the triangle that way. So that's our delta. The delta serves a diverse array of interests, including agriculture, which is originally why these levees were built up here in the 1800s. So there's extensive agricultural activity there. It's a very sensitive environmental area, including the delta smelt, which is an endangered species living there. This is a more detailed map of the delta. The rivers serving it are the Sacramento River and the San Joaquin River. And of course, it's draining out to the San Francisco Bay. This is a major node in our water system. You can't overstate the importance of the delta to our water system because basically everything west of the Sierra Crest, all the precipitation falling in the mountains west of the crest, which is most of it, is draining into the Central Valley and going out to the sea through the delta. Okay, so most of California's water is going out this way. Now, there's an interesting balance going on that our water resource managers deal with every day, which is that we have seawater here and we have fresh water here. The water coming out of the mountains is fresh water, snow melt mostly, and at some point it's running up against the seawater and there's this natural transition zone. Okay? And that has to be delicately maintained at all times. You can never have the seawater penetrating in here because if you did, you would contaminate the water supply that is ultimately going into the California Water Project, and we'll be talking more about that. So let's step back to before the California Gold Rush, before the Delta was any kind of an engineered or even human-influenced system. Might have looked something like that. What you had was channels bringing water from the Sierra down to the bay, just like they do now. Every once in a while, the water in those channels would be a little bit higher in a flood event, and it would go over the top of these natural levees. As it goes over the top, the sediments in that water would initially fall out right near the edge here. Those would be the coarsest ones, and the rest would go in here, the fines, and so on. So what you have are natural levees forming at the edge of these channels. In the interior, very rich material there. You have all kinds of vegetation naturally growing. That vegetation dies, but the ground gets replenished, and so you have this sort of natural cycle of release of methane and carbon dioxide from the dead vegetation, but replenishment with new sediments, and you have this sort of balance in the ecosystem. So then humans come along. Okay, so we have the gold rush. And a lot of people can't make enough money mining gold, and so they come down looking to farm, and they start farming in the Delta. It's some of the richest soil around. And so everything goes great until you get those periodic floods, and then you lose your farm, right? So what you do then is you start building up on top of those natural levees just a little bit. As long as your levee is taller than the neighbor's levee, then when the water comes up, it's going to take care of their farm, lowering the pressure, and you're okay. So there's this little bit of a levee war going on among the farmers. The federal government actually encouraged the development in this area. There was something called the Swampland Act that encouraged reclamation in this area. And reclamation districts start being formed where owners sort of get together and work on their levees, building them and maintaining them. Okay, and so this sort of activity of building up levees throughout the Delta was going on from 1850 through about 1930. This picture is showing a clamshell bucket. So the construction consisted of grabbing soil, whatever's in the channel, and dumping it. And that was about it. So not a whole lot of engineering here. There's no compaction. Just taking the soil and basically dumping it and not worrying too much about tree limbs and things like that that might be sitting there. Needless to say, we would not build it that way today. So what happens is we're building up the levees. And remember that it was overtopping of those levees that was replenishing the interior and maintaining that sort of ecosystem balance. Now that we have the levees, we don't have that anymore. That replenishment is not going on. And so the decay of the organic matter, the soil there is peat, it's organic soil. The decay still happens. It dries out. You're releasing carbon dioxide. The wind comes along and literally blows the soil away. Okay? This would naturally fill up with water. It would be a big bathtub, but of course they pump the water out in order to have that be usable as farmland. So that goes on for a while. This keeps going down further and further and further, and it's basically making the heights of these levees taller and taller, and the gravity stresses are getting bigger in these unengineered systems, and it's not unusual that you have a failure. Okay? So as we look at these rates of lowering of the ground, these retreat rates, they can be as high as 10 centimeters a year. It's something that is easily measurable. And the channels are nearly sea level, and the islands, these interior areas, because of this depletion, are often very far below sea level, as much as 7.5 meters, which is kind of alarming, actually. That retreat, as I mentioned, is contributing to the instability of the levees, and the big instability threat is actually not sliding into the channel, but sliding into these areas over here because of the tall slopes you end up with there. And here's a number to keep in mind. I'll come back to this later. If you add up all the area, all the volume that is below sea level in the interior of these islands, it is 3 billion cubic meters of volume in the interior of these islands. And that is actually a huge number and a very significant number in understanding the risk. And I'll come back to that later. And the thing about it is, this isn't static, right? This keeps getting worse year after year. We're pumping out those islands, the wind blows, the soil lowers. So those levees are getting taller relative to the interior island every year. This is a map that was published actually earlier this year that is showing, this is the scale bar here. The hotter colors indicate lower elevations. -9 would be 9 meters below sea level. This is the delta through here. And so most of the areas, as you can see, are somewhere between, let's say, about 3 meters to maybe 6 meters or so below sea level. And it's quite extensive. These blocks here are the islands I'm speaking of. This big area here used to be an island. The levees failed, and they decided it was too expensive and too much trouble to try to fix it, so they just left it as an interior lake, basically. If you go look out there and you drive along these levee roads, if you can tell here, this is the channel, this is the interior, I think you can see visually how much lower this is than that. And it's really kind of unsettling. It doesn't seem right that the water is above the land. We're used to it being the other way around, right? If we look at the delta today, the little red lines indicate where these levees are. They're actually owned by many different reclamation districts. A few of them are owned by the Corps of Engineers and a few of them by the state, but mostly by individual reclamation districts. Interestingly, while the reclamation districts are responsible for maintenance, when they fail, somehow, and the attorneys can maybe answer why this is, somehow the state, us, are responsible when the levees fail, even though we, as the state, don't own them. Now, levees are all over the world, right? We use levees for flood protection on rivers everywhere, but normally levees are not continuously impounding water. Usually they're there when you have a flood and you want to protect the place. These levees are different. They're actually like dams because they're always impounding water because of that lowering of the material in the interior of the islands. When we look at this entire system here, there's a lot of important spots, but this one here is the key for the California Water Project. It's called the Clifton Court Forebay, and a lot of these levees, aside from protecting the islands, are channeling water through the delta to that forebay, and that's the intake for the California Water Project. So securing a proper flow of high-quality water to the forebay is essential for the state of California. I mentioned that these levees are marginally stable. Levees fail. They fail on clear blue sky days without any earthquakes or any flood event. We don't always know why. Maybe it's burrowing animals or whatever. They're often sitting there at a marginally stable state, and so we can't be too surprised when they fail. So the channel is here. This one on Upper Jones Tract just failed one day in 2004, flooding the interior island here. They came in and fixed it at considerable trouble. It cost $100 million to fix that and restore the area. How did the cars get there? Well, they had to come from, not from that side, right? They had to come from this side. If you look at the historic record, these types of things are not unusual at all. In fact, between 1900 and 2000, there's been over 150 failures from non-earthquake sources in the Delta. Now, one of the controversial things about this is or is not the Delta vulnerable to earthquakes? This is a question on which there is some debate in some parts of the state, particularly the Delta. And this is a map that we prepared with some help from the U.S. Geological Survey showing earthquake risk as peak ground velocity. And it's useful to kind of paint the picture of what's going on. So the plate boundary fault here, San Andreas, is barely on the map. Here's the Hayward Fault and a few others, and these are very hot colors. We expect these areas around San Francisco Bay to be having very high risk. As we move to the east, we get faults with much less activity. The delta is over here, and we're starting to get faults over here with orders of magnitude less activity than the San Andreas Fault. Okay, so I talked about the plate boundary. Some of the local faults in the delta that are particularly important are Midland, Pittsburgh, Clayton, and so on. And the activity of these faults is heavily debated. There are interests within the delta who do not want the seismic hazard there to be a driver of decision making. And the arguments that have been put forward are that these faults are inactive, they're not going to produce earthquakes, and oftentimes the reasoning behind that is, well, I've never felt an earthquake. I've been living in the Delta for 60 years. I never felt anything, so you're telling me there's an earthquake problem? I don't believe you. So we debate these things, and what we're debating very often is the slip rate, which is basically the rate with which one side of the fault moves relative to the other, high enough that it's a problem or not? So I write here the significance of the Napa earthquake, which happened a few years ago on the West Napa Fault here. Turns out that the West Napa Fault has the same slip rate, practically speaking, as the faults further east in the Delta, like the Pittsburgh, Kirby Hills, Clayton, and so on. So if you're going to argue that there is no earthquake risk on faults of that type, then by extension, there could not have been an earthquake on the West Napa Fault. Right? Now, from a scientific point of view, of course, this makes no sense. But this is the type of arguments that I and others have been involved with interests who do not want to recognize the seismic hazard in the delta. Just for completeness, I should mention that this map does not account for the effects of shallow soil conditions, which amplify the ground shaking, so that would actually be elevating the ground motion here, where you have softer soils relative to what I'm actually mapping there. Okay, so we have some significant ground motion. What happens then to the levees? In order to understand that, it's useful to separate cases where the levees are continuously impounding water, acting like dams, from when they're intermittently impounding water, where usually the water is low. So in the delta, they're continuously impounding. As I mentioned before, this is an image that highlights changes in relief. This is one of those islands with the levees around the edge here, and these are the channels. And again, it gives you a visual of how much retreat of the island interior has happened. So that's in continuous impoundment. Here's a more typical levee, just for context. This is in Sacramento, along the river. This is a levee. The river's down here in the channel. This is natural ground. The levee is high and dry, and it's that way most of the time. Because that would be intermittent. It's only going to feel water during an extreme flood event. What happens to levees when they are shaken? Well, one possibility is that you have liquefaction. That's where the soil is losing strength. And when it loses strength, you can have this kind of slumping, or you could have a flow failure. And keep in mind that the water level in the channel is usually about a meter below the crest. So if you're losing height like this, you're going to lose the island. In order to illustrate that, I'm going to show you the results of a centrifuge test that was run of a sandy levee on PD foundation soil, like you have in the delta. We're shaking the ground. The water that was on this side, this would be the channel, is flowing over the top. This is a slowed down image as the levee settled and sort of spread out. So it's an illustration of that failure mechanism. This is the same thing. The earthquake comes along, shakes it. It actually fails very suddenly, and you can see the water flowing over the top. Okay, so that's an illustration of how liquefaction of the levee fill could lead to a failure. That's not, by no means the only problem. These levees sit on this very, very soft peat, and I'll be illustrating for you in a moment just how soft it is. That's the organic soil. And that material can have bearing failures. You can have levees partly sliding. You could even have the levee simply sinking into the ground as a result of volume change in that fill. This next video is to give you a good visual on just how extraordinarily soft this material is. It is really at the extreme of what we encounter as engineers as we look at soils from around the world. This is my colleague Scott Brandenburg. We're on Sherman Island, which is one of the major islands in the delta. There's about 10 meters or so of peat out here. And Scott is, a reasonably athletic guy, but he's certainly not Arnold Schwarzenegger or anything like that. What he's holding on to is a rod with a sampler on the bottom, and he's going to attempt to push that into the ground. Now, there's already a hole that's probably about 2 meters deep. The sampler's at the bottom of the hole, and he's pushing it into previously undisturbed ground. Oops. Hopefully you can hear him.
So we're on Sherman Island. This auger is a 3-inch mud auger. It's down at a depth of 9 feet in the peat, and I'm just going to try and push it down vertically. It's pretty soft.
Yeah. I'll tell him you said that. He'll appreciate it. So that was done as part of an exploration program for a test we actually ran out in the delta, where we built a model levee, which is what you're seeing here. So you can imagine that the levee is going very long distances this way. So this is like a cutout of a levee. This would be the side slope, the top. And whereas an earthquake would be shaking from beneath, we can't generate an earthquake, so what we do is we shake from the top with a shaker. And I'll show you what happens. The point of the study was to see how the soil underneath the levee is deforming as the levee is developing inertial forces and moving back and forth. We were trying to understand the demands imposed upon the foundation soil by the vibrating levee. This too gives a pretty nice visual. So the shaker is getting wound up here. These are counter-rotating masses. As they spin around, they're developing centrifugal forces, which are shaking back and forth in this direction. You'll see them spinning progressively faster, 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 and then eventually they will slow down. The ground here is the same peat that Scott was running the sampler into. And what I want you to notice is you will be able to see with your eye the vibration of the levee and the peat underneath, which is not something we could normally ever see. So notice the vibration that's happening here. It's like being on a waterbed to be next to this experiment. So this is extraordinarily soft ground. And remember, this is what the levees are built on, right? This incredibly vital infrastructure for all of us. So what we as engineers do, someone at the cocktail hour was asking me, what do you do as an earthquake engineer? Well, one of the things we do is we predict ground motion and other risks. But once we have that, we try to figure out more or less fragility. And I'm going to illustrate here for you conceptually what fragility is. This is how strong the ground shakes. This is the probability of something bad happening, okay? And conceptually, it's pretty simple. If I don't shake the ground very hard, the probability of something bad happening is small. If I shake the ground really hard, the probability of something bad happening is really high, maybe even 1. And it's the whole relationship there. As I go from we're good to we're bad, that's called a fragility curve. And engineers want to be able to understand that relationship. In this case, we would be talking about, for example, what's the probability that the levee has enough deformation that it doesn't retain the water anymore and it flows over the top. So we and others are doing work to characterize things like that. I'll just run through a couple of things. It turns out that Japan has had a lot of recent earthquakes and very significant documentation of how their levees have performed. So we actually know what percentage of the time the levees do well and don't when they have different levels of ground shaking. And so this is the result of those kinds of studies. This is an empirical fragility curve based on actual field performance in Japan, although in this case of intermittently loaded levees. They don't have the continuously loaded kind like we do. And you can see when you're getting to ground motion levels of, let's say, about 30 to 40 centimeters per second, you're getting probabilities of failure of, say, 20% or so. And that's about what we're looking at in the delta, those ground motion levels. We also do tests, like I showed you, the field tests and the centrifuge tests, to try to understand the mechanisms by which levees fail and to develop models for the performance. Part of this is we've tried to understand how that peat soil responds when it's sheared. So what we do is we impose some kind of deformation on it, like an earthquake would. And what happens is the peat generates water pressure. So the pressure within the voids is going up, but not so much, actually, less than we thought. As that pressure dissipates following the earthquake, there's a little bit of volume change. But what surprised us in our research, and this is having pretty significant consequences in the state now, is that went further. There was a lot more volume change than just the volume change from dissipating that water pressure. And that's a mechanism that is a little bit complicated to explain, but it's more or less a volumetric creep that is accelerating as a result of the disturbance from the earthquake. And the significance of that is while the levee might settle a little bit from the earthquake, it might then accelerate and settle catastrophically in the weeks following the earthquake. And you only need to lose about a meter, and the levee has failed. Another thing that we're working on, this is where we're working with the Dutch. The Dutch have a lot of concerns with their own levees, not so much earthquake-related, but from storms, is levees are systems. They're series systems. We have what's called a reach. There's another levee here with different reach, another one here, and so on. The whole thing has to work for the island to be protected. You have a whole system, and every part of it needs to work. There could be a certain probability of failure here, let's say 20%. If they're all 20%, the probability that this thing survives is not 20%. It's almost a certainty, okay? So how do we calculate the performance of the entire system, probabilistically, accounting for the fact that there's correlations from one location to another? This is a fairly complex problem that we've been working on with our Dutch colleagues. The outcome of all this is that we have pretty substantial risk to our levee systems in the Delta. We're going to lose some. The question then is, how resilient is it? Because remember, I started out saying it's expected, more or less, that we're going to have losses and earthquakes. Can we recover? Now, this video was created by the Metropolitan Water District and Kurt Schmoody, who's a consultant for them. This is the Delta. This is Clifton Court. This is San Francisco Bay. What it's going to show is an earthquake happens, and as a result of the non-engineered, in many cases, or poorly engineered levees, when the earthquake happens, many different levees fail. So that's what those red dots are indicating. And they're all failing more or less at the same time. So if we look at a blow-up of one of them, it's settling or having a stability failure. The water from the channel flows into the interior of the island. Now keep in mind, we have 3 billion, with a B, cubic meters of volume to fill up. As the image pans out, you see that not just that island, but lots of other islands are failing because so many levees are failing throughout the system. And much of that 3 billion cubic meters of volume is going to be filling up. So where's all that water going to come from? Okay, there's only so much coming from the mountains. You can open up the spigots and all the reservoirs. It can't provide enough flow for that to be fresh water. So the water is going to have to come in from San Francisco Bay, which is an endless source of water, of course, but saline water. And so hydrodynamic modeling of that process, this is basically 8 days compressed to 1 minute, with the hotter colors indicating higher salinity. This is essentially seawater. And you see the tidal fluxes, and the saline water is penetrating throughout the delta and ends up, of course, down here at Clifton Court. So, all right, we have some saline water. You might think no big deal. Let's just bring out a big hose and wash it back out. Okay? Trouble is, there's no water source here. San Joaquin, Sacramento River, there is no water source you can use to flush that out from Clifton Court. So what are you going to do? Well, you can start repairing the levees, so that's fine, but you've got this giant lake in the middle of the island. Windstorm comes along, you get some waves in that lake, it starts eroding the levee from the inside. They don't have any erosion protection on the inside. The water's supposed to be on the channel side, not on the interior. So now you have additional failures from erosion from the inside of all these levees. So you repair one section, and then you lose another one. And the problem becomes almost intractable. Keep in mind, one failure took $100 million to fix. And now we're looking at scores of failures. So the water managers for the state are petrified of this. They're not sure they can ever get this system up and running, or at the very least, it's going to take multiple years. Okay, so this is pretty serious. And keep in mind that it's that delta water that gets mixed with the Colorado River water. So not only do we lose the delta water if we lose the delta, but we lose our current functionality with the Colorado River water unless we build up a whole infrastructure to treat that water, which we don't currently have. So, what are we doing in terms of mitigating the risk? You may have heard that Mayor Garcetti has an effort to increase resilience in Los Angeles, Resilience by Design. You can Google it. So he has a report that addresses a number of earthquake problems within Los Angeles. And among the topics addressed there is the LA Aqueduct. Again, that's not Delta, but it's Elizabeth Tunnel. And there are 15 options that are discussed for addressing the problem with the tunnel. I'll just mention 2 of them. So this is just to highlight one notion that I think is accelerating and will continue, which is let's manage the water we have locally better, including all of our wastewaters. You probably read about this in the paper. We can take our wastewater, we can treat it a little bit, we can basically pump it into the ground, usually near the coast, then we withdraw it further inland. The ground is naturally filtering it, we treat it again, we reuse it. There's actually a lot of water that can be reclaimed that way. So we do have the ability, with some expense, of course, to better use what's already here. They're actually working on this one, so this isn't just a hypothetical. They're putting in a HDPE carrier pipe through Elizabeth Tunnel. It's about this size. It's not enough to supply LA, but it's better than zero. And it's extremely flexible, so when the tunnel is offset by the earthquake, there can at least be some water still passing through there. So that is actually being done now. We have pretty substantial storage on the west side of the fault. So we have, so for these surface aqueducts, we have storage west of the fault so that as they go down and we're repairing them over months, we have water that we can draw from. So this is Diamond Valley Reservoir owned by Metropolitan Water. So this and other reservoirs are meant to give us months of supply so we can have something to live off of when the San Andreas Fault event occurs while we repair our aqueducts. Now with the Bay Delta, it's trickier. What the governor has proposed is this twin tunnel system. Now before I mention that, I should say there is a good deal of political resistance to this from interests in and near the Delta. There really is no viable fix, I would say, with the current levee system because of this continuous retreat of the interior islands, and we really can't stop that. So you can try to repair the levees to the current condition, but they just keep getting worse year after year. So the governor's proposal is to build tunnels that are drawing water from Sacramento River and taking the water down to Clifton Court. These tunnels are not to be underestimated in their significance. They're 12-meter diameter tunnels, 48 kilometers long, costing estimated $15 billion. And just to put that in perspective, these are bigger than the Big Dig in Boston, and they're bigger than the tunnel going between England and France. So these are major engineering projects to try to deal with this problem. Okay, so to summarize, we need a resilient water system. We can accept losses in the short term. We do not want to see something like Katrina where we lose our water supply for an extended period of time because we can't survive as a society without it. We can get by a few weeks. We can't get by for a long time. We could see a depopulation scenario unfold here, and that's what we have to avoid. All our major water supply aqueducts cross the San Andreas Fault. Just the geography of the state. There's no way around it, so that's the reality we live with. When we look at all those aqueducts and how they could be repaired after that event, there are varying degrees of resilience. In every case, the owner recognizes the problem and is trying to do something to prepare for it. As I mentioned with Northridge, there are additional hazards from local distribution systems, and we have pretty good experience with that from Northridge and other events, that it's damaging, but we can recover. When we look at all these different aqueducts, I would argue that the most vulnerable is the California Water Project, for the reasons that I've explained. I should put in context that the San Andreas Fault earthquake, remember it's a 150-year return period, that's pretty frequent in an earthquake world. The earthquakes up in the Delta are much less frequent. It could easily not happen in all of our lifetimes, or our children's lifetimes, or our grandchildren's lifetimes, or it could happen tomorrow. That's the way risk works. It's a low probability event. It's a lower probability in the San Andreas, for sure, but it's going to happen. It's just a question of how long. The water project is essential, both from a volume standpoint, it provides a lot of our water, and a water quality perspective, as I've explained. The water quality is quite good from it. As currently configured, the levees are highly vulnerable, not necessarily to San Andreas events, but to the local events directly beneath. The repair time is uncertain. It's almost certainly very long. They don't even know how long it would take. And I think by any measure, it is not resilient. And this is the problem. Okay, so there is some mitigation being planned. The governor is trying to do something about it, but it's costly, and there is mixed levels of political support. So whether this project actually goes forward depends on who the next governor is, what the priorities are. So we'll see. But at least now, I hope you have a better appreciation for the threat that we face. And I thank you for your attention.